Yeah, so let me first recall a little bit what we were doing last time. We were discussing special situations where a sequence of, say, numbers of combinatorial origin is satisfying a certain recurrence. The recurrence in general, it's just a dependence of the next number in our sequence on a bunch of previous numbers. Typically, the most interesting case is when this dependence is of a finite fixed number of previous numbers. For example, the next number depends on the 5 previous numbers using some rule. Sometimes there appear recurrences where the dependence is on all the previous numbers in the sequence, but these are usually much more difficult to study. And also, the basic case where one can have good formulas and theory is when this recurrence is linear. That means that the next number is just a linear combination with certain coefficients of a bunch of previous numbers, say 5 previous numbers, plus maybe some additional constant. So in other words, the next number is given by a linear function of the fixed number of previous numbers. The coefficients can depend on n, on the index, and then we have time-dependent or index-dependent recurrences. The easiest case appear, of course, when at least the coefficients in front of the previous numbers, not the constant term, but they are time-independent. And then we can find explicit formulas, and that's what we did last time. So this theory is very parallel to if you study, if you learn something about linear differential equations. So this, what we study, can be called as theory of linear difference equations. So we are using differences instead of differentiation. And many aspects of the theory of linear difference equations are very parallel to those of linear differential equations. Okay, so let me share my screen. Hopefully it will work. Yeah, good. So today we'll concentrate on linear non-homogeneous recurrence relations, some aspects of them. But let me first recall a little bit our basic notation and say, so a linear recurrence so is something like some coefficients, say C, 0, say n, plus C1 an minus 1, plus plus ck an minus k equals to some eventually b of n. Or maybe let me put the index where it should be, bn. So in general, so we're looking for the sequence, we're interested in finding the sequence an, our goal. So in principle, those coefficients C can be also dependent on the index, but the easiest situation occurs when they are constant and independent on the index. Then we are talking about linear recurrences with constant coefficient. B, it's much easier if B depends on n, but coefficients C0, Ck, it's much better if they're independent on the index. Okay, so we had if Bn is n for all n, then So let me put asterisk. Then our linear recurrence is called homogeneous. And if not, we'll call it non-homogeneous. So last time we had the following lemma, which would be our starting point here. So one can show that the recurrence, linear recurrence of order k depends on, has a family of solutions depending on parameters. These parameters would be uniquely fixed if we specify the first k elements in our sequence, A1, A2, and so on, AK. If we have done that, then using our recurrence and starting from the index k plus 1, we can recurrently define the next coefficient. So C naught here should be different from 0. Otherwise, we have a degenerate case. It would be recurrence of smaller order. So this is a recurrence of order k. As I said, starting with A1 through AK, if they are given numbers and they will be parameters of our solution, we can, after that, using the relation itself, define AK plus 1, then AK plus 2, AK plus 3, and the whole sequence. Okay, now we had the following statement, which is again parallel, that a general solution of star, which is the non-homogeneous system, equals a general solution of its homogenization. In other words, so we put Bn equals to 0, all Bn equals to 0. So we're looking at the homogenized equation, removing the right-hand side, plus a particular solution of star. So in other words, I'll repeat again that it's much easier to find how to solve a homogeneous recurrence relation with constant coefficients. So finding a general solution of homogeneous system, homogeneous recurrence relation, is usually a quite simple thing. To find a particular solution of non-homogeneous equation works in certain cases. We'll discuss this today, some of it. But in general, there is no recipe how to do it. For an arbitrary sequence Bn of right-hand side, there is no easy way to find a particular solution. But at least we have a reduction. If we're lucky enough and we can find a particular solution which works in several cases, we can find the general solution of our non-homogeneous system as well. Okay, so let me start with a certain example, and we'll be mainly, mainly working today with recurrences of order 1 and order 2. That's a basic example. So recurrence of order 1. So order 1 means that we have something like a n plus or minus some constant an minus 1 equals some given function. But we'll be working on a specific example. An equals an minus 1 plus 3n squared. And here, say we start with, this works for n big or equal than 1, and we start with a naught equal to 7. This would be our starting value. Okay, so let's start calculating things. So we have and we find the sequence AN. We'll see for this specific case and its naive generalizations, we can do this without any serious problem. So what do we have? We have A1 equals okay, 3 plus 7, yes. So n equals to 1, and A naught is 7. Now A2 equals, so we have 3 times 2 squared plus, let's see, plus A1. Yes, A1 is 3 plus times 1 squared. So this 3 times 1 squared plus 7. And again, plus 7. So A3 equals 3 times 3 squared plus 3 times 2 squared plus 3 times 1 squared plus 7. And so on. We get that En, in other words, would be equal to sum k from 1 to n, 3k squared, and to this we have to add 7. Okay? So, which is 3 times sum k from 1 to n, k squared plus 7. So if you remember, we had a formula for the sum. So recall that. So sum from 1 to n k squared is given by the following formula. We did this last time, if I remember correctly. n plus 1, 2n plus 1, 1/6 of that. So we have this formula, and then we can continue. The n would be equal to 3 times this expression plus 7. So it would be n, oops, here is n plus 1, 2n plus 1, divided by 2, and plus 7. Well, this would be a simple situation where we can work out by just plugging and checking and using some summation formula for certain sequences, what our answer would be. So, but in general, things do not work that easily. Let me nevertheless describe a certain situation where we can guess the right-hand side. So where we can guess the general formula. So a special case of recurrences of order 1, which is, so we're looking, say, a recurrence of order 1, say, is in the form an plus some, say, number q. Maybe let me take minus here. Minus q times an minus 1. And then I want it to be equal to some coefficient alpha times some number r power n. So here I want to maybe recall a little bit what we discussed last time about solutions to linear homogeneous recurrences with constant coefficients. So let me make a small detour, recall that. So if I have a linear recurrence with constant coefficient, so we had it C naught an plus C1 an minus 1 plus plus CK an minus k equal to 0. So the idea to solve it, you probably remember, the idea to solve it was to try an equals some r power n, where r is unknown. And then if we do this substitution, we will get a characteristic algebraic equation for r. Then we get c naught r power n plus c1 r power n minus 1 plus da 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 plus ck equals to 0. So which means that r satisfies this equation. I don't know, let's call it exclamation mark, which is the characteristic equation of the linear recurrence. Characteristic equation of a linear recurrence. Okay, and if it turns out that this characteristic equation has n equal to its degree n distinct solutions, then we can at least formulate the general formula which will work over the complex numbers. If, so we had a small lemma, if R1 through Rn are the roots of star which are distinct, then we have the general solution. Then the general solution An is given by sum of with some constants alpha 1 R1 power n plus alpha 2 R2 power n plus da 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 plus alpha k r k power n. And this is a formula for the general solutions. For the general solution of our linear recurrence, if we have distinct characteristic roots. And this is the easiest situation which can happen. So, but if we're interested in real solutions, or we might have some multiple roots, then the formula becomes a little bit more complicated, but not very much. For example, if R is a root of some multiplicity L is a root of multiplicity L in our characteristic equation, then it contributes not just one solution, but L solutions of the form to. So it contributes to, for example, beta R power n, beta maybe 1 R plus beta 2 n R power n, plus and so on, plus beta L n power L minus 1 R power n. So it contributes to a whole more complicated expression, which depends exactly on L parameters, beta 1, beta 2, and so on, beta L. Okay, but so then the last thing we discussed last time is if we have complex solutions, complex conjugate solutions, but we're interested in real solutions to our characteristic equation. This can also be handled, but maybe we can skip it for the time being. Now, with this recollection, let me go back to what I wanted to discuss. Let me rewrite this again. So, a special case of a non-homogeneous equation or recurrence of order 1 is, so we have a n minus q a n minus 1 equals to some rho power n and with some constant alpha. Okay, I want to solve this kind of a relation. Rho is, so these are fixed numbers. And this is just, the right-hand side is just the general first order homogeneous recurrence with constant coefficient q. Okay, so we need a general solution of a n minus q a n minus 1 equals to 0 of the homogenization of this, which is, you probably know better than me, which is a n equals some constant a times q power n. Yes. So this recurrence is equivalent to the next guy, a n equals q times the previous guy. So we have a geometrical progression with some constant. So this constant is a parameter. Now we need a special solution of this recurrence, a n minus q n of the non-homogeneous thing. Okay. Now here, two situations can occur. So here is the new part. So claim if rho is not q, then we can find a special solution as a n equals some new constant beta rho power n. Okay, why? Well, let's make the substitution and see what happens. So we get, indeed, we get, if we substitute this ansatz in our thing, we get beta rho power n minus q beta rho power n minus 1. Okay, and this should be equal to alpha rho power n. Okay, so we can, what can we do? We can rewrite the left-hand side in the following way. So we get beta minus q times beta. So here we have, let's see, sorry. Okay, let me do it once again. So the right-hand side, the left-hand side, I want to rewrite it in the form rho. Okay, beta times rho power n minus, and I want to transform this also in rho power n. So it would be q beta rho power n and divided by rho. Yes. And then I can factor out rho power n, and I'm getting beta can be also factor out times 1 minus q, 1 minus 2 rho power n beta 1 minus q divided by rho equals alpha rho power n. And so we have a relation in which implies that beta can be taken in the form alpha divided by this 1 minus q divided by rho. And this is well defined. This is a well-defined expression. And the only problem occurs if, so notice that we have the requirement, rho is not q. That's why here in the denominator, this is non-vanishing. So we have a uniquely defined beta. Okay, now what happens, so this was our first case A. Now, what happens if rho equals q? Then we're actually in trouble. So in this situation, we have, in other words, we have, what do we have? A n minus q a n minus 1 equals, just to double check, alpha q power n. In this case, indeed, we can still use the general solution of our homogeneous equation, which is again a general geometric progression with the numerator q. What about the special solution? So a particular solution, then, a particular solution can be found in the form, so an equals some number beta n q power n. So we have to throw in an additional factor n. Okay, let's check why it works. Check. I hope I haven't confused anything myself. So we have a beta n q power n minus beta. Okay, we have this factor q here, minus q. And then an minus 1. An minus 1 would be beta n minus 1 and q power n minus 1. And this should be equal to alpha q power n. Let's see if we can find a beta which satisfies such equation for all values of n. Okay, again, we have to, so this guy comes in here. So the left-hand side now would be beta n q power n minus beta n minus 1 q power n. So which is, if we, what do we get here? We are getting, so beta n q power n disappears. What is left is beta q power n. And the right-hand side, is alpha q power n. So the result is that an equals alpha n q power n, and this gives us a particular solution. Of the recurrence. Okay, so we can do it if our right-hand side in the non-homogeneous equation is also a geometric progression. So if the denominator of the geometric progression is not our characteristic root, then it's an easy situation. If it is our root, then we have to struggle a little bit more. Okay, let me work out some specific example for you, concrete example. Maybe concrete examples, a couple of them. So say the first one would be a n minus 3 a n minus 1 equals 5 times 7 power n. Okay, so So what about the homogeneous equation? So the homogeneous recurrence, is an equals 3 power n minus 1, or in other words, an equals some coefficient, some constant a times 3 power n. So this is good because the right-hand side we have 5 times 7 power n. So 7 is not 3, means that we're in the situation where, which is easier, where the correspondent characteristic roots are not the same. So 7 is not 3. So we can find a particular solution of, let me again call it maybe double star of double star as a n equals some constant alpha times 7 power n. Okay, so what is this alpha? So to get alpha, we substitute. Okay, what do we get here? So we have alpha 7 power n equals, oh sorry, minus 3 alpha 7 power n minus 1. This is 3 k n minus 1. And we want it to be equal to 5 7 power n by an appropriate choice of alpha. Okay, how do we do this? Yes, so we have that we want to transform this piece into 7 power n, of course. So we get alpha times 7 power n minus 3 alpha, and I'm multiplying and dividing by 7. And then we have 7 power n minus 1 here. So we, in other words, are getting alpha minus 3 alpha divided by 7 and times 7 power n. And we want this coefficient to be equal to 5. So we get, so first of all, we can factor out alpha here, alpha, and then 1 minus 4/7 equals to 5, which is what, alpha times 4 divided by 7 equals 5, alpha equals 35 divided by 4. So our general answer would be, so an equals, what do we get? A times 3 power n and plus 35 divided by 4, 7 power n. And if we have some initial condition like a1 equals, I don't know, 2020, then we get a particular value for the starting constant a. Okay, so this illustrates our first situation. What about the second situation? So the second situation, okay, the second situation is if we take case 2, let's assume that we have, instead of 7, that we have 3 power n in the right hand side. We have a similar, we have the same left hand side, an minus 3 n minus 1, but now in the right hand side we have 5 times 3 power n instead of 7. This is a more complicated case because again, for the homogeneous recurrence, so we get an equals capital A times 3 power n. But now this 3 and this 3 is the same 3. In other words, the right-hand side is a solution of the homogeneous equation. then we cannot use the same trick as before, but we can, then we look for a particular solution in the form n equals alpha n times 3 power n. And we'll be looking for this constant alpha. Okay, yeah, again, substitute. What do we get? We have now alpha n 3 power n minus 3 alpha. Now we have n minus 1 times 3 power n minus 1 should be equal 5 3 power n, question mark. Okay, so if we factor out alpha, in the left-hand side we get alpha. Now, so we get n minus n plus 1 times 3 power n should be equal to 5 3 power n. Or in other words, alpha should be equal to 5. And now here we have the general answer here would be n is of the form some constant a times 3 power n, as we had before, plus 5 times 3 power n. Sorry, I forgot n here, of course. 5n 3 power n. So this would be our one parametric family of solutions, and then again, given some specific boundary condition, we'll get what we want. Okay. Yeah. So let us discuss a little bit more what we have done so far. So I suggested a specific class of first-order recurrence relations with a very special right-hand side, where the right-hand side is a geometric progression. And then, in this situation, it's possible to find a particular general solution of the homogenized thing is very easy, but we can even find a particular solution for the non-homogeneous, the original equation. And there are two basic cases. The case when this geometric progression is a solution of the homogeneous equation, then it's a little bit more difficult. If it's not, then we can find a particular solution in the form of a geometric progression with the same denominator, but probably a different constant. And if it satisfies the homogeneous equation, then we have to throw in an additional factor n there. So it would be a, n, and some q power n. Okay. So a generalization of those things is called the method of undetermined coefficients. And again, if you have studied linear differential equations with constant coefficients, then you know what I'm talking about. There is a table, C table, on page 479 in Grimaldi. There is a special list of the right-hand sides and the forms in which you can look for a particular solution. Let me maybe recall what kind of situations are there, and this is again the cases which show up in linear differential equations with constant coefficients. You can find a particular solution if your right-hand side is a polynomial in n. You can find a particular solution if your right-hand side is a geometric progression. And in certain cases, you can find a particular solution if it's like sine or cosine, yeah, of n with some coefficients. But we'll talk a little bit more about the special case when we have a geometric progression in the right-hand side. Okay, so let me discuss in more details the case of recurrences of linear non-homogeneous recurrences of order 2 with where the right-hand side is again a geometric progression. So, but for the general case, look a little bit in Grimaldi's this table, and you'll see what other cases can be addressed. And it's not just we can do this not just for order 2, but for general order. But the formulas would be more and more clumsy. So here we'll just let me formulate a certain lemma for the order 2 case, and the right-hand side being an exponential, being a geometric progression. Yeah, so consider a recurrence, consider a linear recurrence of order 2 given by, say, an plus 2 plus some constant c1 an plus 1 plus c naught an equals some constant k times r power n. K is some real number, so we have a geometric progression in the right-hand side with the denominator q. Now I am saying if then we have three situations. Then if if r power n is not a solution of the homogeneous homogeneous recurrence, which is an plus 1 plus c1 and an plus 2 plus c1 an plus 1 plus c naught an equals to 0, then a special solution to, let me call it, I don't know, what, like this, special solution to this can be found as an equals some constant alpha r power n in the same form with probably a different constant than we have on the right-hand side. Okay, now in the second case, if Rn is a solution of the homogeneous guy, again, I probably need to denote it somewhere, somehow, so of that, but n times r power n is not, then we can find a special solution in the form alpha times n times r power n. And finally, if both Rn and n times Rn solve our homogenized thing, then an equals some constant alpha times n squared r power n. And this is it. So these are three opportunities which we have in case of a linear, second order linear recurrence relation, with the right hand side being a geometric progression. So these are only possible cases, and probably we'll have some exercise later on. Okay. So let's see. So let me give you one example, and then we make a break. So specific example, solve. So we have an plus 2 minus 4an plus 1 plus 3an equals minus 200. So what is our situation? So here we kind of have a constant. A constant can be considered as a geometric progression with denominator 1. So we want to understand, first of all, so what general solution the left-hand side has, the homogenized thing. So here let me add with, I will be adding the initial conditions here to get some specific numbers. So I want a naught to be 3000, and I want a1 to be 3300. So this would be necessary to define parameters in our general solution in a unique way. So the characteristic equation, you can probably know, you can probably tell me yourself, characteristic equation would be r squared minus 4r plus 3 vanishes, which is r, what do we get, minus 3 times r minus 1, I guess, vanishes, yes. So the roots are r1 is 3 and r2 is 1. So the general solution, these are two distinct real numbers. So the general solution and homogeneous would be alpha 1, okay, alpha maybe, times 3 power n plus beta. 1 power n is just 1, of course. Okay. So we get this is a general solution. In particular, constant satisfies this equation. So we are in the special situation. So minus 200 solves the homogeneous equation. So we are in case number 2. So we need to look for a particular solution as some constant, I don't know, gamma times n. Okay, let's see what gamma will work for us. So we get, with this ansatz, we get gamma times n minus 4. Oh, sorry, this should be n plus 2 minus 4 gamma n plus 1 plus 3 gamma n, and this should be equal to minus 200. Okay, so what is it that we're looking at? Now the left-hand side would be then, so what do we get? We get gamma n plus 2 gamma minus 4 gamma n minus 4 gamma plus 3 gamma n So gamma n should disappear, and it does. So we have -2 gamma should be equal to -200, which is gamma equals 100. So our special solution is 100 times gamma. So the general solution now is a n equals, what do we get before? 3 alpha, sorry, times 3 power n plus beta. This is a general solution of a non-homogeneous equation, and plus 100n. Okay, now we need to use our boundary conditions to define our constant alpha and gamma. So we get from the initial conditions, what do we get then? So we get a naught, which is n equals to 0, which is alpha plus beta, n equals to naught. This should be equal to what? 3000, yes? Good. Now alpha 1, which is alpha times 3 plus beta plus 100. For n equals to 1, this should be equal to 3300. Okay, let's see. What do I get? If I will be subtracting the second one from the first one, so a1 minus a naught will give us 2 alpha, beta will disappear, plus 100 equals 300, yes. So alpha equals 100, good. And then alpha plus beta equals 3000, so beta equals 2900. So our final answer would be now n equals 100 times 3 power n plus 100 times n, and finally plus 2900. Okay, so now it's a good time to stop here, and then we'll continue in some 5 minutes with the second section 10.4. Okay, good. Small break now. Yeah, and this section is called the method of generating series. Again, it's a certain trick which allows you, in certain cases, incorporate what you are doing in a generating series and work with those generating series as a whole entity, as a function. And this sometimes is quite useful and gives nice answers quite easily. Good. So section 10.4, method of a generating function. So just want to repeat again that in general, it's difficult to solve non-homogeneous reconciliation. One has to be lucky to be able to find closed formulas for the entries of the sequence. So it's difficult to expect such situations, but they can actually occur in practice in some interesting cases. So that's why we try to apply general machinery and see if it works, and then sometimes we're lucky. Okay, so the idea is So the idea is to multiply the equation. Say we have an plus some C1 a n minus 1 plus C2 a n minus 2 plus da 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 plus say ck n a n minus k equals to some bn. To multiply this equation, oops, how do I get away? By x power n and add them. And add all these equations so then yeah, and then yeah, I'll show an example quickly. Is there any technical difficulties? No. Then we usually get an equation involving the generating function, the usual, not the exponential, the usual generating function. How do we denote it? Say f of x, which is the sum, say n equals to 1 or from 0, depending on from where we're adding, n x power n. Okay, so this is a general idea, but let me make a concrete illustration in one or two cases, and I hope it will become more clear what we're doing. Okay. Otherwise, maybe it sounds a little bit odd, but you'll see what we're doing. Example, solve a n minus 3 a n minus 1 equals n. And say a naught equals to 1. So in fact, we know we have already solved it before. So we have a hint, or we can use it once again. So an should be equal 7/4 3 power n minus n half minus 3/4. So we should get the same answer. So this one we should get using the things which we discussed before, namely, so this is this is order 1 relation. So the homogeneous one has a general solution, which is a geometric progression with some coefficient times 3 power n, and then we have n. So we have to look for a special solution in terms of a polynomial of degree 1, and we get this thing. So okay, so let's try to do it, solve it by using generating functions. Okay, so what do? I'm multiplying this equation by x power n. So I have a summation, say from n, here we enumerate, start enumerating from 0. So we get from 0 to infinity. And let's see. So we get x power n times a n minus 3 x power n a n minus 1. And this should be equal to sum n x power n Yeah, maybe we should, maybe, so not, maybe we should start from 1, maybe summation from 1 here. And from 1 to infinity x power. Okay, that's what we did. We multiplied this equation by x power n, and then we're adding over all n from 1. So we have a naught is given to us, but starting from n equals to 1, we can apply our reconciliation. Okay, so if we split the left-hand side into two sums, which is the first sum would be sum n from 1 to infinity a n x power n. This is by definition our usual generating function f of x. Now we want to do something similar to get f of x with this other summation. The other sum would be minus 3 sum a n minus 1 x of x power n. Yes? Okay, so we need to do a small trick here and sum from 1 to infinity. Yes? So let me factor out n here. Yeah. So if I, not n, I'm sorry, x. So if I write this is minus 3x, now n would be from 1 to infinity a n minus 1 times x power n minus 1. This is almost what I need, but this starts also, so it looks, this thing looks like a naught, yes, because we are starting summation from 1 to infinity, and here is a minus 1 plus a1x plus a2x squared plus da da da. So everything is nice except for we have this a naught here. So okay, so the left hand side would be then f of x, which we're happy about, minus 3x. Now a naught, we know this is 1, and this, the second part, this long sum is again f of x. So we have 1 plus f of x. So we were able to rewrite the left-hand side completely in terms of f of x, which we are very happy about. Now the right-hand side is summation n from 1 to infinity n x power n. Okay. So what is that? So the right-hand side here is can be obtained from, we know actually what this thing is. It's x divided by 1 minus x squared. Why is that? We did this example in one of our earlier lectures. If we take the generating function of the geometric progression 1 plus x squared blah 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 blah, we'll get 1 divided by 1 minus x. If we differentiate it once, we almost get this with a small shift, and to compensate this shift we have to multiply it by x. So if you I hope you remember still. So in other words, let's see. So 3x. Yes, so what I'm getting is f of x minus 3x minus 3x f of x equals x divided by 1 minus x squared, or in other words, f of x times 1 minus 3x equals this thing. So f of x equals so, and if we fiddle a little bit with this formula, we'll get the required answer for the coefficients. So we'll get the same result as we obtained by other methods, the same formula for the coefficients. So I think I'll leave it as it is at the moment, just to compensate, just to save some time. Okay, now I want to work out with a different example, which is also quite nice, and then hopefully we'll do some exercises from the end of section 10.4. So the other example I want to go through is also in your book. It's very, I think it's quite illuminating example. Is rederive the formula n plus n plus r minus 1, choose r for the number of choices of R objects from a pool with n types of objects with repetitions. So we got this formula earlier by introducing an additional markers. So saying that if we have n types of objects where each object appears unlimited number of times, and we want to choose R objects from this pool of n different types with repetitions, then we'll get this binomial answer by thinking as follows. So first we take object number 1. Some number of times we're allowed to, so not more than R. Then when this object will fill this object as many times as we want under our limitations, and then we throw in an additional divider. So here where the object number 1 stops. Now we do that with number 2, and after number 2 we put its additional divider, and so on and so on. So we have to throw in R minus n minus 1 additional dividers. So after the first object, after the second, and so on, after the n minus first object. So then we can reinterpret our problem as, so we have a stack, we have now n plus r minus 1 positions, and we have to put n minus 1 dividers somewhere at some places, and we'll fill the remaining empty spaces by our objects. First we put to the left we'll put our object number 1, and in between the first and the second divider we'll put the object number 2. Between the second and third we'll put the object number 3, and so on. So that's how we got this answer. But now I want to get the same answer by using recurrences and working with recurrence relations. Okay, now the first thing we observe is, so first we want, so how do we get the recurrence? Okay, so we get the recurrence in the following way. Okay, B1. Let's see. just 1 second. So the recurrence would be as follows, and so let me write it, and then we will look at it and realize that this is true. So hint A of n and r. So this number we are looking for is equals A of n minus 1 and r plus A, plus A of n and r minus 1. Okay, how do we get this? So the idea is, so we're choosing r objects from n different types. So we are thinking, okay, so I think we're considering objects of the first type. So if we're looking at objects of the first type, so we can divide our situation in two sub-situations. So either there are no objects of the first type. Do I make sense? Let's see. Minus 1. Yes. Yes. So either there are no objects of the first type, and then we have n minus 1 types remaining, and we still need to choose our objects in between n minus 1 types with repetitions. Yes. So this is this thing, this contribution. Or we have an object of the first type. We're choosing this. Now we have one less objects to choose, r minus 1, and we still can use all n types for that. And this gives us this second contribution. Okay, good. Now, yes. Now, so this is a recurrence relation dependent on two positive integers, yes, and n and r. So we have kind of a double recurrence with two indices, in other words. So let me introduce the generating function fn of x would be the summation. So we fix n, and we'll be adding with respect to variable r, like this. N is fixed here. So our running variable would be only r, and we'll be summing from 0 to infinity. A n r x power r. Okay, now then our recurrence. So what do we have additionally? We have the boundary condition. Condition is a n of 0 is 1. If we're not choosing any object, if we're choosing 0 object, then there is just one way to do this. And now, then we'll have our recurrence will transform in the following relation. Fn of x minus a of n0 equals fn minus 1 of x minus a of n minus 1, 0 plus x fn of x. In other words, using our boundary condition as well, we'll get at fn of x equals fn minus first of x divided by 1 minus x. So now for n equals to 0, notice that f0 of x is just there is just one choice for any n to choose objects from 0 types. So it's very natural that if 0x is just function identity 1, which implies that we get for fn of x, we'll be getting this simple nice formula, 1 divided by 1 minus x power n. And yeah, we work this out if we expand it, or we use Taylor expansion maybe, or we use the products of the expansions of the geometrical series n times and so on. So is the coefficient in front of x power r, we'll get this n plus r minus 1 over r, x power r, and this is the coefficient we were looking for. This would be our a n r. Okay, so this was the other way to derive the same formula. So this would be the end of the lecture, maybe, or maybe we can do a couple of examples, at least one example, maybe. Let's see if I find something good in the book before we finish. So section. So let me maybe do one exercise from section 2.3 and maybe one exercise from section 2.4. Okay, let's see. So section 2.3, let's see, maybe what is it? So solve the recurrence. So this is exercise 5, Solve the recurrence an plus 1 plus 3an plus an plus 2 plus 3an plus 1 plus 2an equals 3 power n. And the boundary conditions, so n starts from 0, and we have a naught is 0 and a1 is 1. Okay. So let's see if we can do this. So first of all, we have to look at the characteristic equation of the homogeneous guy and see if it has a root 3 or not. If it doesn't, then the situation is easy. If it does, we have to work harder. Okay, so the characteristic equation would be so we get r squared plus 3r plus 2 should vanish. So what is it what we get? I think it's r plus 1 times r plus 2. So our roots are minus 1 and minus 2. So a general solution an homogeneous would be some constant minus 1 power n plus some other constant minus 2 power n. So this is not a solution of the homogeneous thing, so it's an easy situation. So we can find a particular solution as n is some coefficient alpha have you say gamma times 3 power n. So we'll be looking for gamma. Okay. To do this, we have to substitute this in our recurrence, and we'll be getting, so the left-hand side would be then gamma 3 power n plus 2 plus 3 gamma 3 power n plus 1 plus 2 gamma 3 power n. And we want this to be equal to 3 power n eventually, but let me first rewrite it a little bit. So I want to get 9 gamma 3 power n. I'm taking away power 2 here, plus I'm taking away 1 power here, again 9 gamma 3 power n, and finally plus 2 gamma 3 power n. So the whole would be 20 gamma 3 power n. Now this, the right-hand side, as before, it was, whatever was it, 3 power n. So we get 20 gamma equals 1, gamma equals 1 divided by 20. So we get the general answer for the non-homogeneous would be, let's see. So we have an equals alpha minus 1 power n plus beta minus 2 power n. And finally, plus 3 power n divided by 20. Now we need to satisfy our additional conditions. Alpha 0 is 0, alpha 1, A0 is 0, and A1 equals 1. So what does it give in our specific situation? So if n equals to 0, then we get alpha plus beta plus 1 over 20 vanishes. Oops, vanishes. And if a equals 1, we get minus alpha minus 2 beta, and n equals 1 plus 3 divided by 20. This should be equal to 1, and I hope you can handle and find out alpha and beta from this system yourselves. Okay, let me take one exercise from the last section, 10.4. See something fairly easy, hopefully. Let me try to solve by using generating functions. Okay, so let me take an plus 1 minus an equals n squared. So n is bigger or equal than 0, and a naught should be 1. Okay, let's see. So let me introduce so f of x would be summation k from 1 to infinity a k x power k. Yeah, or maybe use index n here as well, just not to confuse things. And yeah, so we'll be multiplying this equation by x power n plus 1 and add. So what do we get? Let's see. So the first equation would be just, so our first equation would be a1 minus a0 equals 1. So a2 minus a1 equals, so 1 squared, 2 squared. A3 minus a2 equals 3 squared, and so on. So we'll multiply this guy by x, this guy by x squared, this guy by x third, and so on. And together we get, and add them up, we get totally x a1 plus x squared a2, which is f of x. Now we'll be getting minus a naught x minus a1 x squared minus a2 x cubed, and this should be equal to 1 squared plus 2 squared plus 3 squared plus, and so on. Yeah. So we have f of x minus, now, so first of all we have to factor out x from the second thing, and then we'll be getting a naught plus a1x plus a2x squared plus This should be equal sum k from 1 to infinity I forgot to multiply by the powers of x here, I'm sorry. X squared, x cubed, and so on. So the right-hand side in this case would be, let me write it, if I factor out x, I'll be having 1 squared plus, let's see, do I need to do that? Okay, x2 squared plus 3 squared x cubed plus 4 squared x to the 4 plus, and so on. Okay, so the left-hand side, and a naught was 1 here, yes, so what do we get? So we have f of x minus x minus x f of x. Now what about the left-hand side? The right-hand side, which is 1 squared x squared plus 2 squared x squared plus 3 so so we have seen this function, but I don't remember it by heart now. F of x 1 minus x and minus x. So the left-hand side is clear, but the right-hand side, so let's see, we got it. So the right-hand side, so we start with 1 minus x, which is this thing. Then we differentiate it once. We'll be getting 1 plus 2x plus 3x squared plus, and so on. We'll be multiplying it by x. We'll be differentiating it again. Oops. And we'll be getting almost what we want. And finally, we have to, so this is this is x times the first derivative. So if we'll be differentiating this thing again, so we'll be getting almost what we want, and then we'll have to multiply it by x to get the final answer. So that's so that would be what is required to get the right hand side. But the answer is in the book somewhere. Just don't remember it by heart. And then if I denote this answer by, say, phi of x, which is a very specific function, so f of x would be phi of x plus x and all divided by 1 minus x. Okay, so we got our generating function in this way, and then just, yeah, fiddling with this a little bit, we'll be able to get the coefficients of the series, which gives us our answer for the AN. Okay, so this is it for today. I hope I made some sense to you. And yeah, so I'm stopping my lecture today, and will be posting it in maybe half an hour. Okay, good luck. Bye-bye.